Now, a very good evening, everyone. Welcome to the class. The discussion topic for today's class is the continuation of the discussion that we started yesterday, that is on colloids, colloidal dispersions. If you have gone through whatever we have studied, I have shared the video link also. I think you have gone through that. In case of dispersions, the dispersions are classified into different types. The types of dispersions are colloidal dispersion, molecular dispersion, force dispersion. It is based upon the different type of parameters on which the classification is done. The classification, when it is done dependent on particle size, is classified into force dispersion, which is bigger in size compared to colloidal dispersion, which is smaller in size, and molecular dispersions, which are further lower in size. Now, after that, the dispersions are also the colloidal dispersions. This is the classification of dispersion. Dispersions are classified into different types by size, by the affinity of dispersed phase and dispersion media. Say, for example, by the affinity or interaction of dispersed phase and dispersion media, they are classified into, you have to remember this, they are classified into lyophilic and lyophobic. This is the based upon the affinity towards the solvent system. The system is lyophobic when it is solvent repulsive nature, and a system is lyophilic when it is having solvent attractive nature. Likeliness to the solvent is lyophilic, repulsiveness to the solvent is lyophobic. This classification is based upon the interaction between the dispersed phase and dispersion medium. Now, these solvents, if you replace it with water, then this classification again can be termed as hydrophilic colloids or hydrophobic colloids. Hydrophilic means it is having water-loving nature. Hydrophobic means it is having the heating or repulsive nature towards the water. This is the classification of dispersion system based upon the interaction between the dispersed phase and dispersion media. Again, the terms I am repeating, it is lyophobic, hydrophobic, and lyophilic and hydrophilic. Now, when the dispersion systems are classified based upon the particle size, they are classified into molecular dispersion, which are very, very fine dispersion systems. When the dispersed phase is very finely divided in pico to nano range, 10 to the power minus 12 to 10 to the power of minus 9 range, when the particle size of the dispersed phase is present in the dispersion media, that is known as molecular dispersion. Now, bigger size compared to molecular dispersion is colloidal dispersion, where the particle size ranges from nanometer to micrometer, 10 to the power of minus 9 to 10 to the power of minus 6. Okay, 1 nanometer to 1 micrometer, then it is going to be said as colloidal dispersion. Now, then if the particle size further increases or the larger particles are present as dispersed phase, then this type of dispersion systems are going to be termed as force dispersion, where the particle size is more than 1 micrometer. More than 1 micrometer, then it is going to be said as force dispersion. Okay. Now, this is based upon, this classification is based upon what characteristics? Based upon the type of particle size, or depending upon the size of the particle size. Now, the colloidal dispersions are also sub-classified into different types. Yes, I told you last day, colloids, example I told you, blood is a colloid, blood which is circulated, which is the fluid connective tissue of our body, largest fluid connective tissue of our body. Blood is a colloid because different type of blood cells are distributed uniformly as dispersed phase in the dispersion medium. Now, after that, other than blood, if you take the example of pharmaceutical dosage forms or formulations, then aerosol is also a colloid. Now, aerosol means what? Aerosol is a pressurized system which depends upon the intensity of the gas to expel the product concentrate. Example of aerosol, yesterday I have told you, shaving foam. The foam that we use is also an aerosol, and the Polini spray or the move spray that is there on our normal deodorant, that is also a aerosol. So aerosol, you know, in your note that I will be supplying you, you have to please note the note that I will be supplying you that contains a table. That table you have to remember the classification of colloids into aerosol. Say for example, solid in gas is also an aerosol, and liquid in gas is also an aerosol. Wherein solid in gas means solid is the dispersed phase and gas is the dispersion media. Subsequently, liquid in gas means liquid is the dispersed phase and gas is the dispersion media. So both of them are aerosol, different type of aerosols, and other types, say for example foams. Foams means you have to say so gas in solid or gas in liquid. These are foams. Now sol is also there. Solution is different term, sol is different term. S-O-L, sol. So sol means what? Solid is the dispersed phase which is dispersed uniformly throughout the dispersion media, which is liquid. So you have to remember sol. Sol is not similar to that of solution. Solution is homogeneous, sol, SOL is heterogeneous, sol. Sol is also a type of colloid. Now, in case of sol, the finely divided solid, say for example, precipitates may be uniformly distributed. The precipitates in finely divided state may be uniformly distributed in the dispersion media. Say for example, a water-based system or some solvent-based system. So that type of dispersion is going to be termed as sol. So sol is also a colloidal dispersion. So you have to remember gel. Gel is also a what to say colloidal dispersion. So different type of colloids. Classification of colloids, you have to remember aerosol, there are sub-classification, foam, there is sub-classification, gel, there is sub-classification, and sol, there is also sub-classification. The table is there in the note which I will be supplying you. You can go through that and you have to remember. Okay, so this is all about the classification of the both dispersion systems as well as the colloidal dispersion. Dispersion systems, I will again repeat, dispersion systems are classified into molecular dispersion, colloidal dispersion, force dispersion. They are also classified depending upon the interaction between the dispersed phase and dispersion media into lyophilic and lyophobic or hydrophilic and hydrophobic dispersion. Now, if you talk about the classification of your colloidal systems, the colloidal systems are classified into different types. I told you that aerosol is a type of colloidal system, colloidal dispersion. Again, there are subclasses of aerosol, subclasses of foam, subclasses of sol, and also that of your gel. So you have to go through the what is the dispersed phase and what is the dispersion media. You have to go through that particular table in order to remember it. It is very important because it is an important part of your syllabus. Now, moving forward, yesterday's class we have discussed thoroughly about different things like introduction to the dispersion system, then the colloidal dispersions, then the different properties like we have discussed about the size and we have discussed about the shape. Then shape, I told you that it is spherical in nature. Most of the colloidal dispersions or the force dispersions, because very sphericity is there. Observe. Then size is, I told you that size distribution. Particle size is in a particular range of distribution. So I think you remember that, which we discussed yesterday. And then we move forward to different other parameters like your what to say, the kinetic properties. Kinetic properties which we discussed about the Brownian motion, the zigzag movement of the colloid particles within a system. That is Brownian motion, which was the term was the principle or the property was studied by Sir Robert Brown, and he carried out his initial study when he observed the pollens which were suspended in water. So through that, it was not a straight movement left to right or top to bottom. It was a zigzag movement. So that study was done by Sir Robert Brown, and he termed it as the Brownian motion. Then we studied about the in yesterday's class we studied about the diffusion, the movement of the particles from a higher concentration to lower concentration in case of diffusion. And also I told you about the osmosis, which is from lower concentration of the solvent to higher concentration through a semi-permeable membrane. And I also told you about the osmotic pressure, that is the pressure across the pressure gradient across the semi-permeable membrane, which is responsible for the movement of these substances from one zone to another zone. That is known as osmotic pressure, which is denoted by pi. So certain formulas will be there in your note. You have to go through that. And after that, we went into the what are the other properties? Like we studied about the sedimentation, the concept of Stokes law, the equation that is B is equal to 2 pi square rho 1 minus rho 2 small g divided by 9 eta, the viscosity, the role of viscosity, how it plays an important role in determining the rate of sedimentation in case of the dispersed systems, and also what is the role of the difference in the density between rho 1 and rho 2. If the density differences are more, the settling will be more. And also I told you the concept of the radius or the diameter of the particle in the formula of Stokes law. So these all things we have discussed in our yesterday's class. And then we move forward to certain other discussions like how to prepare the colloids, the different instruments which are available. I told you by application of the shearing forces, by using colloid mill, the dispersions can be prepared. Colloidal dispersions can be prepared, or force dispersions can also be prepared. And also I told you that by using the rhapsonic homogenizer, which uses the concept of, or the principle, it is based upon the principle of utilizing the ultrasonic waves in order to generate the regions of compression and rarefaction, whereby the larger globules are simultaneously broken down time and again into smaller sized globules. So these all things we have discussed in our yesterday's class. So I am moving forward from there onwards. Certain other things also I told you, you can review the previous video lecture for your understanding purpose. So today's class starts from here. We are going to start from the optical properties of the colloidal dispersions. Now, if you remember last class, we discussed a little bit about the Tyndall effect and the light scattering. Tyndall was the scientist who studied the scattering of light when it is passed through a dispersion system. So, when a beam of light, an incident light, or a beam of incident light having certain intensity is passed through a colloidal dispersion, three things can happen. That is what we have learned in our yesterday's class. Number one, what can happen? Number one, the light may be absorbed, which will result into giving a certain color to the colloidal dispersion. The degree of the intensity of light which is absorbed will result into generating certain amount of color into the dispersion. Now, this is one thing with, which can happen to the incident beam of light. Number one, I told you absorption. Number two, it may be scattered. So scattering of light is very important, and we are going to learn about what is the role of scattering of light. So scattering of light is very important, and the scattering of light has been studied by the scientist Tyndall, and he said the scattering of light can be utilized in order to determine the size of the particle. Okay, so scattering of light is the second thing, and the third thing is the transmittance of the light. So three things can happen to the incident beam of light. Number one, absorption. Number two, scattering, and number three, transmittance. So under these circumstances, second parameter, which is your scattering of light is very, very important, because when the light gets scattered, what happens in case of the colloidal dispersion? More the size of the particle. Through the study, it has been found out that more the light is scattered, that means the size of the particles are more. Now, scattering normally takes place at a right angle position. Suppose if you are entering the beam of light horizontal position, the scattering will be vertical. Or if you put it from vertical position, the scattering will be at 90-degree angle, it will be horizontal. So, scattering of light and all this, you can go through that particular formula which is given in your book. For example, the formula is I equal to I0 exponential to the power tau and L minus tau L. So I is what? I is the transmitted radiation or transmitted light. I stands for transmitted light. I is equal to I0. I0 is the incident beam of light having certain intensity, and which is equal to, so that means I means what? I is transmitted light is equal to the incident beam's intensity, I equal to I0 exponential to the power minus of tau L. Tau means turbidity. I told you whenever the light is scattered, it results into turbidity of the dispersion. So more the turbidity, that means larger size particles are present. So you have to remember turbidity is the main thing in case of light scattering and optical property of colloidal dispersions. I repeat, turbidity is the main thing. Turbidity in this equation is denoted by tau and minus L. So minus L is also there. Minus tau L. So tau is turbidity and L is the length of the travel of the light. That means how much sample it is. Suppose sample it is this much. So this much length when it is going to be considered. So that is the length of travel of that particular incident light. I will again repeat the equation. Tyndall effect says what? When an incident beam of light is passed through colloidal dispersion, three things can happen. Number one, it can be absorbed. Number two, it can be scattered. And number three, it can be transmitted. In case of absorption, change in color observed. In case of scattering, what happens? Turbidity of the solution, turbidity of the dispersion takes place. And number three, in case of transmittance, it will straight away pass through that. So what is the implication in this particular case? More the particle size, more will be the scattering of the light. So that can be directly related by using this particular equation. This phenomena was studied by Tyndall, and this scattering of light is known as Tyndall effect. The formula is I is equal to I0 exponential to the power minus tau L. I is the transmitted light, I0 is the incident light's intensity or the beam's intensity, and minus tau means tau stands for the turbidity of the solution which was resulted because of the scattering of the light. And length, L is the length, which is the length of the sample. The light has traveled how much distance. So these things you have to remember, and then from this, by using this particular experiment, it becomes very easy to determine the particle size of colloidal dispersion. Now saying so, it is theoretically very easy to determine it by using the light scattering method, but experimentally it is very a little bit different. It is little bit difficult. How it is little bit difficult? Because when you take a particular sample and you keep it for analysis, by the time you keep it, you have to preserve it properly. Just imagine a situation when a colloidal dispersion is there and some foreign particles, fines or mist or dart falls on it. So if the fine particle or the mist or the dart is falling on it, the results will be not accurate. It will not be the results of only the particles which are present in the colloidal dispersion. It is whatever foreign particles are into it. So whether finding a particle size by using this particular method, that is the light scattering method, you have to be very careful that no foreign particle falls on the colloidal dispersion. Otherwise, the results will not be accurate, and the results which will be produced will be inaccurate. So this you have to keep in mind. By utilizing the same theory, the concept of light, you can also find out the molecular weight, and the molecular weight you can find in the formula. It is given by Debye equation, D by E, Debye equation, which takes into consideration the radius as well as the molecular weight of the particle. By putting these values in this particular equation, you can also find out the molecular weight. Now I will repeat it this much. I will repeat it again. Optic properties. In case of optical property, you can determine the particle size by light scattering method by using Tyndall effect. By taking into consideration this particular formula, I equal to I0 exponential to the power 9 tau L, and more the scattering of the light, the dispersion will be more and more big, and particle size can be easily calculated. Only thing you have to keep in mind that no foreign particle comes and deposits on the surface or enters or penetrates into the colloidal dispersion. And if you are interested to find out the molecular weight, you can do that also by using the Debye equation. Now moving forward, in optical properties only, when we move forward, say for example, you want to determine the particle size. So you have determined it. Now you want to observe the shape. So you can utilize an optical microscope. Now, optical microscope, colloidal dispersions are very difficult to view or find out the particle size. Particle size determination by using optical microscope of your colloidal dispersion is very difficult, but you can always determine the particle size of pore dispersion by using optical microscope. But what you can do in case of colloidal dispersion by using the optical microscope is that you can observe the zigzag motion, that is the Brownian motion. When in case of the colloidal dispersion, against a black background, the colloidal dispersions are kept as a sample against a black background. Sorry. What happens immediately? I told you that the colloidal dispersions are always in the randomized zigzag motion. So this zigzag motion can be easily observed by using the optical microscope. Now, if you want to see more effectively the shape of the particle, then you can go for ultra microscope. Ultra microscope. In case of ultra microscope, you can see the particle shape as well as size. In case of colloidal dispersion. Further, you want to increase your efficiency and intensity of viewing, then you can go for using the electron microscope. Electron microscope very efficiently determines the particle size as well as the shape of the colloidal dispersion. Am I clear? Electron microscope. First is the normal optical microscope. Secondly, I told you about the ultra microscope. And thirdly, I told you about the electron microscope. By using an electron microscope, what you can do is that you can easily see the size and shape. Now, there is a drawback of electron microscope when we talk about the colloidal dispersion. That means this electron microscope can easily determine the or identify the size and shape of the dried substances. If the sample which is under study is dried, then you can easily use the electron microscope. But you very well know that the colloidal dispersions are not every time dry, and they are liquid also, gaseous also. So therefore, in order to find the configuration, this problem arises in finding the configuration. See, you can always, I again repeat, don't get confused. By using electron microscope, you determine size and shape. But in order to find the configuration of the colloidal dispersion, scanning this electron microscope is not much effective, because electron microscope cannot find out the configuration of the liquid sample. It can only find out the electronic or the configuration of your dried sample. So if you want to get a three-dimensional diagram of your dispersed particle, or if you want to get the configuration of that particular dispersed phase, then you need to use scanning electron microscope. That is SEM. Scanning electron microscope can be very easily utilized in order to determine not only the size, shape, but also it can determine the configuration of the dispersed phase in the dispersion medium. I repeat once again, the optical microscope, then I told you about ultra microscope, then I told you about electron microscope. Electron microscope, very easily you can determine the size and shape, okay, but the configuration, you will find it difficult. This electron microscope can only determine the configuration of dried samples, but if the sample is liquid or some other medium it is there, then you have to use the scanning electron microscope, which can easily determine the size, shape, as well as the configuration of the dispersed phase in the dispersion medium. So this is all about your optical properties of colloidal dispersion. These all things you have to study. Okay, light scattering, the Tyndall effect, then the Debye equation in order to find out the molecular weight. Then you have to study about the optical microscope, what are the utility of optical microscope, then ultra microscope, then electron microscope, and lastly, what is the advantage of scanning electron microscope, which is commonly known as SEM. Okay, now moving forward, this is optical properties is done. Now when we move forward, kinetic properties last day we have already discussed. Now we are moving forward into the electrical properties. Now electrical properties means what? The charge that is carried by the colloidal system. The charge which is carried by the colloidal system. Now ionization or ionic dissolution. If we talk about ionic dissolution, see any electrolyte if you consider, electrolyte contains both, in case of electrolytes, the presence of both and ions also present, and cations are also present in case of electrolytes. Now you talk about, say for example, a colloidal dispersion, and this particular colloidal dispersion can carry a surface charge. So this is classified under or categorized. The topic is electrical can carry a surface charge. Now, surface charge can be either positive charge or it can be negative charge, and the charge depends upon the proportion of cation or the anion present. Now, these are which to uncertain. One of them is silver Ag and another one is iodine. Silver, as you know, Ag plus, so it is cation, and iodine, as you know, I minus, it is anion. Now consider both the cases. Number one case where the iodine proportion is more, so the surface charge which it will be carrying will be more or less on the negative side, more on the negative side. So therefore, if the concentration of iodine is more, then it will be carrying more of negative charge. Now, if the proportion of silver in silver iodide is more, then it will be carrying positive charge, because silver Ag is positive and iodine is negative. In case of silver iodide, if iodine proportion is more, it will be carrying negative charge. In case of silver iodide, if the silver proportion is more, then it will be carrying the positive charge. So these charge differences are also observed in case of colloidal dispersions. Charge differences are also observed in case of colloidal dispersions, and they are termed as surface charge or surface boundary charge. In boundary between the two phases, the charge is always present. Now, this is also termed as surface potential. This is also termed as surface potential. Similar type of activities, you can take another example of metal hydroxides, for example, aluminum hydroxide or magnesium hydroxide. In these cases, the two anions and cations are hydrogen cation and hydroxide anion. H plus cation, OH minus hydroxide anion. So these again determine the surface charge of the these metal oxides. Like your magnesium is the metal and oxide, so magnesium hydroxide or aluminum hydroxide. So therefore, the surface charge or the presence of the surface charge is always there. Ionization. So you can go through little bit about the electrical properties of the colloidal dispersion. More and more detail if you want, then you can study it. The presence of electrical bilayer or double layer, that is also given in the book. If you are further interested, you can study it. Electrical bilayer, that is also there. Okay, surface charge, surface potential, then the bilayer, that is the double layer charge or the potential, that also you can study. So this much, these are the different properties of the colloidal dispersions. Now we are going to move forward in our this chapter with the discussion on two more parameters or two more points. You will find it in your book, peptidization, and coacervation or coalescence. So what are they? And lastly, the protective colloids. Peptidization and coacervation or coalescence, and then the protective colloids. So let us discuss one by one. Peptidization means what? Deflocculation. Deflocculation means presence of the particle as individual entities. Deflocculation or peptidization means what? Say for example, a precipitate of a certain compound is there. Freshly prepared precipitate of a certain compound is there. Say for example, ferric hydroxide, FeOH3. Ferric hydroxide is a precipitate. Now that particular precipitate, you can easily subdivide it into finely sized particles in a dispersion medium. So that is again the case of sol. I told you solids dispersed in liquids. So when the precipitate of ferric hydroxide is finely divided and dispersed in the dispersion media, and this phenomena is known as peptidization. And this utilizes the concept of one particular thing which you have to always remember, the presence of common ion. Might be a little bit confusing, but again when I repeat, you understand it very slowly. Peptidization or deflocculation is the process by which salts or colloidal dispersions are formed. How they are formed? A precipitate which is there can be finely subdivided into a dispersion medium. Precipitate forms the dispersed phase, and when it is finally subdivided into the dispersion medium, by utilizing a common ion. Okay, that is known as peptidization, and that is also a method for formation of colloidal dispersions. Okay, so this is broadly termed as solids dispersed in liquids. Solids dispersed in liquids. Here the solid is the precipitate and the liquid is the dispersion media. Okay, now in your note which I will be providing, you will find that, remember this ferric hydroxide, it is a precipitate. Now uh, when you mix or stir, rather let me use the term stirring. When you stir ferric hydroxide with ferric chloride, okay, FeOH3 is ferric hydroxide and FeCl2 is ferric chloride. So what is the common ion between both of them? The common ion is Fe, which is iron. Okay, so that results into formation of, from the precipitate, it will immediately subdivide into very finely divided particles of the ferric hydroxide. Ferric hydroxide, it will no more remain as a precipitate, but the same ferric hydroxide precipitate will finally subdivide into very fine particles of ferric hydroxide. Okay, ferric, the charge it carries, the iron is carrying positive charge, so it will be throughout the dispersion, that is the sol. In this particular case, it will be positive charge, positive charge, positive charge, positive charge, positive charge, everywhere positive charge. Earlier it was a precipitate, and now small, very finely divided in the colloidal size range, it will go and it will form the colloidal dispersion. This particular technique is known as peptidization. Okay, so you have to remember the presence of common ion is very important in order to finally distribute the precipitate into the dispersion medium. Now you can, if you are interested, you can take other examples also. Say for example, silver chloride. The formula is AgCl2 or AgCl. Yes. So silver chloride, when it is the silver chloride is a precipitate. Okay, AgCl is a precipitate. Okay. Now silver chloride, when it is that particular precipitate can again converted to the colloidal dispersion, and colloidal dispersion is a type of salt dispersion as well, salt dispersion by using hydrochloric acid. So what is the common ion between both of silver chloride and hydrochloric acid? Is Cl. This chlorine, when you state with the hydrochloric acid, that the precipitate gets finally subdivided into the silver chloride as dispersed phase, uniformly distributed throughout the dispersion. I guess I am able to clarify you very clearly regarding what is colloidal dispersion in case of sol, and the term or the terminology over here which we are discussing is peptidization. Now once you have understood peptidization, the next thing that you need to understand is coalescence. What is coalescence? Now coalescence, whenever it is observed, coalescence means two small liquid droplets are there, for example, and in between them a surface boundary layer is there which is separating it into the individual entities. Just imagine of a dispersion system, let it be coarse or colloidal dispersion, in which, suppose emulsion, let us take oil in water emulsion. In case of oil in water emulsion, oil in finely divided droplets is uniformly distributed throughout the water as dispersion medium. Now, one oil droplet is separated from another oil droplet by a surface boundary layer, and this surface boundary layer does not allow both the liquid droplets to come together and join or unite or coalescence. Are you understanding? So these surface boundary layers play a very important role, which does not allow both the liquid droplets to come together, coalesce and form larger particles. If they form larger particle, what will happen? The size will increase. If they form larger particle, what will happen? Size will increase. If the size increases, then you know the particle size is directly proportional to the stability of the dispersion. In what term? Sedimentation. If particle size increases, coalescence. Because of coalescence, then what will happen? The more and more settling phenomena will be observed. So coalescence is not at all good. So you have to always prevent coalescence. So I think in your different segments, in different subjects also you have studied, by addition of wrong electrolyte. By addition of wrong electrolyte, they may result into changing the phase volume ratio. That means the dispersed phase may become dispersion media, or the dispersion media may become dispersed phase. Isn't it? Now you consider the two cases. One colloid is added with or mixed with another colloid having difference in the what to say, the electrical properties, the what electrolyte. Yes, difference in electrolytes. Now one of them is positively charged, another one is negatively charged, or say for example one of them is hydrophobic, another one is hydrophilic. So if you by mistake mix both the colloids, one of them is hydrophilic, another one is hydrophobic, so there is interaction between them instead of compatibility issues. So because of the interaction, what will happen? One of the phase, suppose dispersed phase, will continuously mix together in order to coalesce and form larger size particle, and it may get converted into the dispersion media. So therefore coalescence is not good, or flocculation. Coalescence is also may be termed as flocculation. Flocculation is not good. So you have to always subdivide the particle size. Subdivide the particle size, and for that deflocculation is very, very essential. Okay. So therefore the particles coming together, overcoming the surface boundary layer is not at all good. So therefore in case of colloidal dispersions particularly, you have to be very, very careful that there should not be any type of interaction because of addition of wrong type of electrolyte. Wrong electrolyte addition should not take place. You should have a thorough knowledge which type of electrolyte is required to be added, and that electrolyte only always you should consider additional purpose. And lastly, the last topic of this particular chapter which is left is protective colloids. So protective colloids are very much useful. You can see which offers protection to the colloids. Which offers protection to the colloids. Now you can say it prevents the creaming and the sedimentation. Now for example, if you consider suppose a hydrophilic colloid system, hydrophilic colloidal dispersion, in which a natural polymer, for example, gelatin is added, or you can say cellulose. Cellulose is also naturally occurring polymer. So these polymers do what? These hydrophilic polymers, when are present in the hydrophilic colloidal dispersion. Hydrophilic polymers means what? They are both soluble in water. Cellulose is soluble in water. It has affinity towards water. So therefore, when this gelatin and your the cellulose derivative polymer, which are both hydrophilic polymer, are present in the what to say the hydrophilic dispersion system. So they do what? They increase the stability. So they do not allow the particles, because they are soluble. Because they are soluble, they allow the other particles, the dispersed phase, to remain finely distributed throughout uniformly. So they do not allow them to coalesce. So these is another property which is observed in case of colloidal dispersion. These are all not colloid, the protective colloids. Protective colloids does what? It protects the colloidal dispersion from coalescence, and it prevents it from what to say, this instability issues. So these are all the topics that we have discussed in our today's class. So you need to go through. Are you hearing, all of you?
Yes, sir.
Yes, sir.
Yeah. Let me rewind the total class, whatever we have discussed. So this is the very summarized way I have tried to explain you. I hope when you will go through the notes, it will be very easy to read and understand. Okay, reading and understanding will be very easy. I repeat, different things we have discussed. I'm not going to repeat whatever we have learned in our last class. I'm simply going to repeat whatever we have learned in our today's class. Now we started with the different type of optical properties. The optical properties, for example, determination of particle size by use and shape as well by optical instruments can be done. So one of the type is the light scattering method, that was studied by Tyndall. So light scattering, the degree of scattering the more and more scattering is because of the presence of larger particle size of the dispersed phase. So more and more scattering, more will be the turbidity. So tau factor will be more. So through that, more the intensity of the light, the incident beam when it is falling on a sample, and if the scattering is more, that means what? It is more and more, the particle size is more, and you can put it into the formula I equal to I0 exponential to the power minus tau and L. I told you tau is here turbidity and L is the length of the sample, how much it has to travel. So three things can happen with the incident beam. One of them is absorption, another one is transmission, and number three is scattering. Scattering over here is the most important because through scattering we can determine the particle size. And we have to be only very careful that no foreign particles come and fall on the colloidal dispersion under study, because the foreign particle which is deposited may also result into further scattering. So the results may not be accurate and it will be inaccurate results. Now if you want to find out the molecular weight can be also found out easily by the same light scattering experiment using the Debye equation. So Debye equation you can find out in the note which I will provide. So that equation if you follow, you can easily find out the molecular weight. Now, in order to determine the shape, the optical microscope is there. Optical microscope, the Brownian motion can be observed. Then the ultra microscope, the size of the colloidal dispersions can be observed. Then electron microscope, the size and shape of the colloidal dispersions can be observed. But the configuration cannot be observed if the sample under study is liquid. In case of dried sample, electron microscope can determine the configuration also. But if it is liquid sample, then you can choose, other than going for electron microscope, you can choose this scanning electron microscope. SAM will give you very clear-cut idea and image. Very nice image is obtained by using SEM, and the image will give you not only idea about the size, it will predict the shape as well as the configuration also. Now, this is all about the optical properties. After that, we have discussed about the what is that? The
Electrical properties.
Yes, yes, thank you. Electrical properties. In the electrical properties, I told you the surface charge is present. The surface charge is because of the presence of the different type of the ions. It can be positively charged surface. It can be negatively charged surface. The more the negative ions are present in concentration, then it will be negatively charged surface. If the positively charged ions are more in proportion, then it will be positively charged surface, and this is known as surface potential also. And this is also observed in case of metal hydroxides also, hydrogen and hydroxide. I also give an example of silver iodide with the silver Ag plus and I minus. Iodine I minus more in proportion, then it will be carrying a surface negative charge. If the proportion of silver is more, which is a cation, then it will be carrying a positive surface charge. And the surface potential, this is also known as surface potential. And the bilayer, the electrical bilayer, you can also study in the note I will be providing. And after that, we moved into what to say? We moved into the baptization.
Baptization.
Yes, baptization. That is a method which utilizes the formation of salt by finally from a precipitate. From a precipitate, that particular precipitate, if you finally subdivide into the finer particles, and it becomes the dispersed phase in a dispersion media. But only condition is that the presence of common ion must be there, and if the common ion is there, that common ion breaks up what? The precipitate. For example, I told you ferric hydroxide FeOH3, when it is treated with ferric chloride FeCl2, the common ion is iron, which results into the formation of earlier ferric hydroxide was precipitate, but now the ferric hydroxide has converted into salt. And if it has converted into salt, that becomes a colloidal dispersion. Likewise, other examples also I told you. I think about one more example, hydrochloric acid was there, silver iodide. Silver chloride. Yes, silver chloride is a precipitate. That silver chloride precipitate, by stirring with or by addition of hydrochloric acid, the common ion here is chlorine, and then that converts the silver chloride precipitate into silver chloride salt. And if it is getting converted into silver chloride salt, then it becomes colloidal dispersion. And the type of colloidal dispersion will be salt. You remember in the beginning of the class, I told you you have to remember the different classification of colloidal dispersions. Colloidal dispersions are subclassified into aerosols. They are classified into, yes, aerosols. In aerosols also there are subclassifications. Solid in gas, liquid in gas, both are aerosols. So you have to study about both of them. And then I told you gels are also there, foams are also there, and sol is also there. So all of them are the different type of the colloidal dispersion. Then we discussed about volumes. When the surface boundary is overcome, then two dispersed particles of the droplets come together to form a larger particle. Smaller particle forms a larger particle. Then this phenomena is known as coalescence. Coalescence means burning the surface layer into different particles. Okay. Now, when that is observed, that result that is not acceptable. So it is observed certain times. So you have to be very careful that such type of phenomena does not take place, because that will result into instability of the colloidal dispersions. Okay, because if the size increases, the size is directly proportional to the weight, and if the weight is more, difference in density will be more.
Sir, your audio is muted. Sir, your audio is muted.
This is there. And after that, we have discussed about the protective colloids. These protective colloids helps in preserving the colloidal dispersions and helps it to offer more and more stability to the colloidal dispersion. So this is all. It is a very simple chapter to go through and understand. I think with this, the total physical pharmaceutics 2 403T paper of your PCA syllabus 4th semester is complete. In all regard, only the note of this particular chapter I have not provided. I told you yesterday I will be providing it very shortly. So if any question you have, you can ask it. The class is open for discussion. Are you present, everyone?
Yes, sir.
Yes, sir.
Please raise
Yes,
your
sir.
voice.
Yes,
Too much,
sir.
too much. Your side. Please raise your voice if you have any doubt. Anyone, any doubt? Any doubt? I repeat again, any doubt is there? Your second sessional exams are also coming, so we have to fix the syllabus also. We discuss with the CR, and then I will let you all know.
Sir, what will be the approximate date of the second session?
This is not the right forum to discuss that. Anyways, the CR will get in touch with the head of the department, and sir will direct, and according to his direction only, we will conduct the second internal examinations. Okay. If you want to ask me anything, then you can ask me about the syllabus. But that also I told you that syllabus I will provide only after discussion with the CR, who will be representing the opinion of the whole class. Is it clear?
Okay, sir.
Is it clear, everyone?
Yes, sir.
Yeah. Then I think that's it. No more classes will be conducted, only in the classroom that we are. I will share the notes. Okay. I will share the notes. Okay. Then everyone, stay home, stay safe. Good
Yes,
night,
sir. Thank you.
everyone.
Thank you,
Yes,
sir.
sir.
Good night,
Nice,
sir.
sir. Nice, sir.
Yeah, yeah.